we have many risk factors that have consistently been shown to be related to atrial fibrillation. Atrial fibrillation itself, type, burden. We have atrial myopathy, cardiac myopathy with its multiple components. But for us, it's difficult to see what their relation is and to quantify this relation. And therefore, our hope is that biomarkers, which per definition should be objectively measurable and can quantify biological processes or pathological processes, can help us understand the incidence of atrial fibrillation, its progression, and all its outcomes. For the sake of time, I'm going to focus on incident and prevalent atrial fibrillation, do not go into outcomes. And indeed, and I will also focus on blood-based biomarkers for now. And indeed, over the last decade, we have put a lot of effort into understanding biomarkers related to atrial fibrillation. And we have looked into different pathways, inflammation, remodeling, cardiac stress, cardiac damage, injury, necrosis, renal function, among multiple other biomarkers. And what we usually saw is that, and we have done this exercise for a data set of 15,000 individuals of the Gutenberg Health Study, that we just took all the variables that were available, including biomarkers, and put them into a machine learning algorithm, and what came out was NT-proBNP at the top. Before echocardiographically measured atrial size, enlarged atrial diameters, and even before age. And what you get here is, Uli showed a similar picture, is a ranking. You do not have a relative risk or hazard ratio, which you can generate by these analyses, but you have a ranking, and you see clearly that NT-proBNP is the most prominent marker. And if you do this prospectively, we did this in a European consortium with over 31,000 individuals from the general population. Again, use a machine learning algorithm adapted for prospective, for analysis, for incident atrial fibrillation. We again see, and here it's the way around, the biggest dot here and the darkest red again is NT-proBNP. The second one then is age, because we know that age is a very strong predictor, then high sensitivity troponin and all the other biomarkers. We had put in 13 biomarkers that had been measured in these individuals. So again, it's NT-proBNP, which is the strongest marker in relation to incident atrial fibrillation. We can also use genetics, and this is only an introductory slide. Michael will talk a little bit more about that, but if you take all the genetic information, and these are common genetic polymorphisms across the genome, so genome-wide polygenic risk scores, and you put them into 100 units, then you see that the individuals in the upper 1% have an increased risk of more than 4.1-fold of having atrial fibrillation. And this might be another way to risk stratify individuals, for example, for improved or better and more intensive screening. But what we do, and this is why I introduced genetics here already, is that we said, how does genetics compare with NT-proBNP? And in the FINRISK cohort with 7,000 individuals, again, incident atrial fibrillation, we looked at a genetic risk score we built here, which comprised 145 SNPs, single nucleotide polymorphisms, that have been related to atrial fibrillation, have been validated. So it's not a new score, but it's really known genetic polymorphisms, common polymorphisms. And what you see if you have here age in quartiles and the genetic risk score in quartiles, you see that by quartile the risk increases, by age quartile the risk increases. But if you exchange the genetic risk score by NT-proBNP, you see, and this was really astonishing, that you have almost the same risks if you look at NT-proBNP and age in the same predictive ability. And the discriminatory ability measured by the C statistic was almost the same if you used genetics or if you used NT-proBNP, a marker that can be measured in routine care. But let's go further, and this is work done by the Groningen group, and they looked at multiple biomarkers, 92 biomarkers, in this case in patients with heart failure with reduced ejection fraction and heart failure with preserved ejection fraction. And here it's a little bit hard to read. is individuals with atrial fibrillation and heart failure with reduced ejection fraction and individuals in sinus rhythm. Again, the same here, atrial fibrillation and sinus rhythm, the red ones. And what you can see is a fairly clear picture that in individuals with heart failure with a reduced ejection fraction, there is a very homogeneous association of these markers. They were measured by a multiplexing technique, and they had been selected for their predictive ability of adverse events in cardiovascular disease. And you see that all these are more abundant in the individuals with atrial fibrillation. And so their conclusion was that atrial fibrillation in heart failure with reduced ejection fraction may be a marker, an indicator of disease progression and more severe disease. On the other hand, atrial fibrillation in heart failure with preserved ejection fraction shows a very scattered picture. And you can clearly imagine that atrial fibrillation in these patients compared to those patients must be some kind of a different disease. It's not the same as in both diseases, heart failure with reduced ejection fraction or with preserved ejection fraction. So this is also a very nice way to use biomarkers to get a better understanding of the pathophysiology of disease. The Birmingham group and the Catch Me consortium, they performed another analysis using similar biomarkers, and they compared classical statistics and machine learning algorithms. And this is also our experience that for now, they seem to fit in very well and to replicate each other. So this top marker here was B-type natriuretic peptide. So we are a little bit, happy that we can confirm that BNP remains the strongest biomarker, which also shows that these newer algorithms, such as machine learning, seem to perform well in our samples. And they also had the opportunity to identify and robustly show that a potential novel biomarker, fibroblast growth factor 23, may be another marker that needs further consideration for atrial fibrillation prediction. But why should we stop with the classical assay-based measured biomarkers with multiplex measured biomarkers? Why don't we go even further? And this is our attempt in Hamburg that we say, why don't we use as much information as possible? Why don't we take genetics, transcriptomics, proteomics, and metabolome that we can measure in blood and in tissue samples? And why don't we compare those and try to really identify novel biomarkers that may go beyond B-type natriuretic peptide, beyond natriuretic peptides? It's a lot of work, and we are only taking the first steps here. This is an example. We looked at preoperative atrial fibrillation, so prevalent atrial fibrillation, and incident postoperative atrial fibrillation. We combine for now only, it goes step by step, transcriptome and proteomic analysis. And what we could see is multiple patterns, and you cannot really interpret them by just looking at them. You need help by bioinformaticians, and they do not identify or tell us single biomarkers, but for now they give us some pathways that may be related. And what we found is not surprising, but we need to go deeper into that. Preoperative atrial fibrillation, there were different patterns compared to postoperative atrial fibrillation. And for preoperative atrial fibrillation, we could demonstrate that pathways with mitochondrial dysfunction and structural electrical remodeling were more pronounced versus postoperative atrial fibrillation. And I think this goes along again with our pathophysiological understanding, was more driven by inflammatory pathways and pathways related to autoimmune response. So a huge field that can be explored and that needs, of course, to be later on validated and put into functional context with the disease. So for now, I think it is important to say that we need biomarkers to quantify atrial fibrillation subtypes, if you want, for risk assessment, for diagnosis, to assess prognosis. And for now, I must say that the strongest and most robust biomarker has remained anti-proBNP, or the atrial natriuretic peptide, which is not widely measured, so the natriuretic peptides. We need to explore novel methods like unbiased biomarker selection models, including machine learning, Also big data analysis, which is part of it. Novel biomarkers are needed to further improve discriminatory ability. There are emerging biomarkers. We also have genetics. Omics is a promising field, but overall, in the future, we need large-scale validation, hopefully also in clinical trials, which will provide the strongest evidence, and the stroke stop study will show how natriuretic peptides or BNP can be validated by being used in clinical trials. And this is the strongest evidence we can generate. So it's still an open field with a lot of future work that needs to be done.